Well, thank you very much for the introduction, and thank you for the Deshpande Center for the kind funding and for the opportunity to present here. My name is Aly Eltayeb. I'm a PhD student in chemical engineering. I'm here to talk to you today about a technology that we're building to capture carbon dioxide efficiently from any gas. So let me just start with the big picture of what we're trying to achieve. We're really trying to change the economics of carbon dioxide capture. There are trillions of dollars of assets of industrial sources or power stations that generate carbon dioxide from 5 to 15% all over the world. And in every possible scenario, they're going to be around with us for the next 30 to 50 years. And they're going to generate enough carbon dioxide to reach every threshold for climate change. So one idea that we're interested in is how about we can capture that carbon dioxide and use it in carbon dioxide enhanced oil recovery to generate oil that has a low marginal cost and has about a third of the carbon footprint. And this is actually not something that's completely new. Parts of it already exist, and that's part of the nice thing. But enhanced oil recovery today, which I'll discuss in a second, uses a very interesting source for carbon dioxide. They actually drill in the ground to look for pure sources of carbon dioxide to use in enhanced oil recovery. And the reason they do that is capture technology is just too expensive. So let me just give you a quick primer on carbon dioxide enhanced oil recovery. This is your average oil well. Only 10 to 20% of the oil comes out under natural pressure. Then you need to start pumping something. You can pump in water with other chemicals, and you can take out up to maybe like a third or 2/3. But then that leaves a third to 2/3 of the oil inside the oil well. This is an oil well that you've already explored, drilled, and produced. The marginal cost of producing oil from it is significantly lower. So every time you hear about an oil company, drilling in the Arctic or looking in the deep ocean, you have to think, why aren't they getting the oil out of the rest of the oil wells? And if you use carbon dioxide, you can generate up to 2 barrels of oil per ton of carbon dioxide. So today, 5% of US oil production comes from carbon dioxide enhanced oil recovery, but the source of carbon dioxide today is looking for pure natural CO2. We think we can unlock the potential to about 60 billion barrels if we can find a way to capture carbon dioxide easily from existing sources. So why is it so expensive to capture carbon dioxide? Let's take a quick look at the state-of-the-art technology, thermal amine scrubbing. This is a legacy technology from the 1940s that's been very effective at capturing carbon dioxide in the natural gas industry. The way it works is pretty simple. Graphics are a little screwed, but the way it works is really simple. You have carbon dioxide in a mixture. You capture it with a solvent, which is straightforward. You form this carbon dioxide solvent complex, which is very stable. You've only solved half the problem. Now you need to find a way to regenerate the solvent and get your pure CO2. The way it's done today with this existing technology is you add lots and lots and lots of heat. You add enough heat to raise the temperature to a point where you break the bond between the solvent and the carbon dioxide. You add this heat in the form of steam. And the end result is a process that looks like this. On the left, you have an absorber, a tower that operates at low temperature. On the right, you have a desorber, a tower that operates at really high temperature, that's driven by steam that consumes about 50 to 80 kilojoules per ton on an electrical basis. Because of how much steam you need and how much utilities you need, and because of the high energy consumption, the end result is a capture cost that's between $60 to $80 per ton, about $20 to $40 above the cost of pure natural CO2. So we've made a slight change to this technology. EMAR is short for electrochemically mediated amine regeneration, if you're curious. We've made a small change to this technology. Instead of adding heat to break this carbon dioxide solvent complex, we add metal ions. These metal ions have the ability to strongly form a complex with the amines, with the solvent, and release the carbon dioxide. And then we have a really simple way of removing these metal ions. So on one side of this electrochemical cell, you generate the metal ions at an anode. They go in, they extract, they do their job, and then you extract them out on the cathode and take them out to regenerate the solvent. This all occurs at almost an isothermal temperature, and it can happen at 50 degrees centigrade or 30 degrees centigrade. The way this looks on an industrial scale, you still have this absorber where the carbon dioxide is captured by the solvent, but to regenerate the solvent to get the pure CO2 stream, you use these electrochemical cells that are operated at low temperature and are driven by electricity instead of steam. And because that's much more targeted, the separation, because you're only targeting the metal ions and not the entire solution with your energy, the energy consumption is down to 25 to 50 kilojoules per ton. And you've also eliminated the need for steam because this is electrically driven, so the technology is sort of plug and play and easily deployed in an industrial context. And the capture cost that based on our current calculations, is between $20 to $35. So it can be almost a third of existing carbon capture technology, and definitely below the threshold of $40 per ton for pure CO2 today. So far, we've built bench scale systems. This is a proof of concept system that we've built. It's an electrochemical cell. It's roughly the size of maybe like a quarter of the table you're standing in front of. And we've been able to demonstrate capture and release of carbon dioxide by applying potential. So on your right in the graph, you apply potential. On the left, you capture CO2. You take out the potential, you just stop capturing, you apply the potential again, you capture again. And we've been able to do that on large different scales of prototypes. And what we're doing now is trying to optimize the performance of the cell to reach the maximum performance before we try to increase the scale. We've been very lucky with the funding we had. So this project originally came out of ARPA-E grant in 2010, followed by Department of Energy funding to further increase the performance and generous funding from MITI. We've also been very lucky with the funding from the Deshpande Center and the Mass Clean Energy Center, where we won an award. We've also had some media buzz from the Boston Globe and the MIT Tech Review, but my personal favorite is that we made it to Reddit, which I think is a big deal. So in terms of industrial approaches, we've been able to build one collaboration so far in the power sector industry with an engineering partner to further develop the technology and explore different chemistries and explore opportunities for demo. On the oil and gas side, we're exploring international partners to look for enhanced oil recovery opportunities, as well as offshore natural gas opportunities, which is kind of another niche application for us. And we're seeking partners, investments, and demo projects, basically. So let me take you really quick through the technology development milestones. Basically, this project started in 2010 through an ARPA-E grant, where we developed a proof of concept and filed some patents. And then in 2013, we had follow-on funding from the Department of Energy, which allowed us to dig deeper into the science and follow up with patents. And through the funding from the Deshpande Center and the Mass Clean Energy Center, we've been optimizing the prototypes, building bigger and better performing prototypes, and also trying to validate the energy and cost performance to show that we're ready to go to the next scale. And we're hoping by 2017 that we'll be able to build demonstration units that we can actually deploy on a field and really explore scale-up. And one quick thing about scale-up, usually when people think about chemical technologies, they think about this really rough transition from something that happens in the lab to something that happens on a large scale. For our technology, there's a slight difference. It's kind of similar to solar cells or batteries, where if you want to increase the scale of the technology, you just add more and more units rather than redesign key units. So if you get the key unit stack right, increasing the scale is just adding more and more units. So that makes it slightly easier. All right, let me wrap up. So basically, this is a carbon capture technology that can enable cost reduction of carbon dioxide from any gas stream significantly and enable us to use it in enhanced oil recovery, competing with natural carbon dioxide and unlocking the potential to cheap oil that has a very low carbon footprint. And we do that through having a technology that's plug and play and easier to deploy and also has a much lower energy consumption. And we've so far been able to build proof of concepts, and we're looking at building demo units for the next step. Thank you very much for your attention.